Hello, I'm Brian Homerding. I'm a performance engineer at Argonne National Lab, and today I'm going to give you a brief introduction to the Kokkos and RAJA programming models. These are performance portable abstraction layers from the DOE National Laboratories. First, I'll give you some introduction to Kokkos, and second, I'll discuss RAJA. I'm going to provide a brief interview and then go through some examples of using these programming models on some of the basic parallel kernels. The aim is to get you started in trying these programming models yourself. To begin with, I'll talk about the Kokkos ecosystem. These slides have been provided by Kristen Trott and the Kokkos team from Sandia National Laboratories. So what is Kokkos? Kokkos is a C++ programming model for performance portability. It's implemented as a template library on top of other programming languages such as CUDA and OpenMP, and it aims to be descriptive and not prescriptive. It also includes some expanding solutions for the common needs of modern science and engineering codes. These include math libraries that are based on Kokkos and tools that support the way that Kokkos performs parallel execution. Kokkos, like RAJA, is open source and available on GitHub for anyone to use. Shown here is an overview of the Kokkos ecosystem. In the middle, we see the Kokkos core. This includes the abstractions for parallel execution and parallel data structures. This is where the primary programming model comes in. But outside of that shows the wider ecosystem, which includes the Kokkos kernels, which are math calls and graph calls, the Kokkos-Tools, which is support for debugging, profiling, and tuning, and additionally the support, which includes documentation, tutorials, and face-to-face boot camps. The Kokkos development team now is across many national laboratories, including here at Argonne. Now, Kokkos core has two primary sections of abstraction, data structures, and parallel execution. These define the where and how to perform your computation. The data structures are broken down into memory spaces, memory layouts, and memory traits. And the parallel execution concerns itself with execution spaces, execution parameters, and execution policy. Shown here are many of the Kokkos core capabilities. As you can see, there's parallel loops, parallel reductions. You can do tightly nested loops and non-tightly nested loops. There's also support for data transfer and atomics, along with many, many other capabilities. Here gives you a brief overview of many of these things. I won't be able to discuss most of them in this brief introduction, but you can always find more information from the documentation online or by going through the tutorials. I do want to walk through an example of a conjugate gradient solver. This is used inside the MiniFE proxy application, which is available on GitHub. And there are three math operations that we're concerned with: vector addition, a dot product, and a sparse matrix vector multiply. And throughout this proxy application, the data management is handled with Kokkos views, as shown here at the bottom. So for our first kernel, we're going to look at AXP. This is a simple data parallel loop, so we're going to use a Kokkos parallel 4. This is very easy to express in most programming models. It's basically the introduction to parallel programming. Shown in the middle is the serial implementation, where we loop from 0 to n, stepping, doing an alpha times x and a beta times y into z. Shown below it is the Kokkos implementation, which is largely similar but has some key differences. To start with, we give it a parallel pattern. Here we're using parallel 4. Next, there's the string label. This is used by profiling and debugging to help simplify identification of kernels. Because Kokkos is implemented with templates and C++, without this, your profiling information would provide long templated names that have C++ mangling within them, but with this, you're able to get a very clean output. Next, we pass in the execution policy, which is simply the number of iterations we're going to do, n here. And then we have an iteration handle. This is the integer index in which you'll access. The loop body is the same, with the small change that we're now using parentheses to go into our views, as opposed to the normal arrays that were in the original code. And those are the minor changes that are needed to implement a basic parallel for in Kokkos. Next, I want to talk about dot product. This is, again, a simple data parallel loop, but with a reduction. So now we're going to use a Kokkos parallel reduce. This is non-trivial in CUDA due to the lack of built-in reduction support. Shown again in the middle is the serial implementation, where we initialize our reduction variable sum. We iterate over 0 to n, reducing into our sum variable. Now, the Kokkos implementation is shown below, and it looks very similar to the way that the parallel for worked. The changes is now that we're doing a reduction, we have a parallel reduce instead of a parallel for. And instead of just passing in our iteration index, we also pass a second variable to the lambda, which is a thread local reduction variable. And then our loop body stays the same, and the sum gets finally reduced into the x.y value, which we use as our final solution. Next, I want to go into the third math function from the MiniFE proxy app. This is the sparse matrix vector multiply. This gives us an example of a non-perfectly nested loops. So first, we're going to have a loop over rows, and then we perform a dot product of the matrix row with a vector. Also of note here, we have some random access into the vector as x is accessed indirectly. So first we loop over our matrix rows with the outer loop, then we perform some work, and then finally do an inner dot product of the row with the vector. So to turn this into Kokkos code, we go to this next code segment. Begin with, we fire off a parallel for, but now we pass in a team policy, which allows for team parallelism over the row work sets. The team policy will take in as a first parameter the size of the league, or the number of teams, which is calculated here. Second parameter would be the size of the teams. This you can pass auto to have Kokkos automatically determine it. And finally, we pass in a vector width. Now inside of the team policy, we're able to use a parallel for with team thread range, which takes the team that you're currently operating in as a parameter. And finally, we perform our row times vector dot product with a parallel reduce using a thread vector range, once again passing in the team that we're currently operating on. One other interesting note here is on the top, as you see with the X view being passed in, we have an additional parameter to the template, which is memory traits. This is telling the compiler that this is done through random memory access, which can enable optimizations such as texture effects on CUDA. Here's some of the performance that was achieved on the CG solve across the various kernels that we just walked through with two different sizes. In the top, we see our performance from the NVIDIA P100 and an IBM Power 8. Now, the programming models that have been looked at are OpenACC, CUDA, Kokkos, and OpenMP. This refers to OpenMP 4.5, OpenMP Target. As you can see, the OpenMP version is not performing very well, but this is because support for the OpenMP Target is very immature at this point. Well, the OpenACC, CUDA, and Kokkos versions are all performing quite well. In fact, the Kokkos version is very competitive with the CUDA version and sometimes does, in fact, outperform it. On the bottom, we have Intel KNL, such as the ones on Theta. And here we see, as higher is better with the gigaflops, we have OpenMC, OpenACC, Kokkos, OpenMP, and some thread building blocks performance data. Looking at the Kokkos performance, we find that it's performing very well in line with OpenACC across all of the different kernels that we had walked through earlier. There is more variation on the KNL between the programming models, but Kokkos does perform well. Next, I'd like to give a little more information on the Kokkos kernels that I briefly mentioned in the overview of the ecosystem. They include BLAS, Sparse, and Graph kernels that are built on top of Kokkos and using Kokkos views. When available, they call into vendor-specific libraries, so you can get that fully optimized MKL call. And they also have a nice benefit of having a simpler interface. This is because the views contain size and stride information already, so you do not need to pass this into your BLAS calls. Shown here is a traditional BLAS call, and on the right is the Kokkos kernel call. And since you're passing in these views, you do not have to pass in all the additional information. I will mention that the interface to call Kokkos kernels is also available at the Teams level inside of a CUDA block, such as this example shown here. I would additionally like to provide you with some more information about the Kokkos tooling support. Now there is profiling support, which is directly inside of Kokkos or can be used with third-party vendors. Additionally, there is auto-tuning, debugging, and static analysis, all under development. So to touch on the profiling and debugging support, as I mentioned earlier, the kernel names that are passed in, the string parameters, into our parallel fors, are hooks to pass on the names. These get hooked into various profiling tools, such as vtune, and it provides a much cleaner look at the kernel in question. Shown here on the bottom, we see that we have a parallel for named AXPB, and this is quick to identify, and we can tell what it is. There's no need to recompile to be able to use these runtime hooks, or to be able to use this profiling information. Now I'd like to provide a little more introduction on the Kokkos. The Kokkos profiling and debugging support is kind of expanded on here. We see that using these string parameters that get passed into various profiling tools give us much cleaner output. Shown here on the bottom right is a parallel for with AXPB. This provides us a clean way to identify our kernels inside of our profiler output. Without this, you'll have a long mangled name with very many templates, and these are easy to use and do not require a recompile. You simply need to set an environment variable to use a runtime hook. There's integration with various third-party tools, including Tau, Caliper, NVVP, vtune, Poppy, and there's plant support for additional ones. I'll quickly mention that HPC Toolkit has special functionalities for models like Kokkos, but it's operating outside of this callback system. Now shown below is an example from Tau, and we see that the Kokkos parallel for gives us a very clean output as to where we're running and what kernel we're looking at. Whereas down below you can see a brief example of what these would look like without the kernel naming, where you have a very long template parameters, which largely would get cut off by the amount of screen with your GUI. Under development is the Kokkos-Tools static analysis. It uses Clang tidy to check for Kokkos semantics. Under active development, and if you're willing to contribute this, we're happy to have your help. Now, shown here is an example of this. We have a couple of notes from the static analysis that lambda capture is modifying a reference variable that's local, which is most likely going to be a bug in your code. Briefly give you an overview of the kind of projects that are using Kokkos. There's currently, as of the time of these slides, there were about 12 production codes running real analysis. Additionally, we get up to around 35 total codes when you talk about the codes that are actively porting or committed to using Kokkos. And then the packages included in large collections such as dpetra and Melu and Trilinos are committed to using Kokkos, and they're actively porting, which brings us up to around 65 projects. And then if you include additional proxy apps and projects which are evaluating the use of Kokkos, they estimate that there's around 100 to 150 different packages that aim to use Kokkos. Now, these users are spread around across a variety of institutions and national laboratories, some of which are shown here. I will talk briefly about the future. So it's publicly announced that DOE is going to be having a variety of HPC resources with different vendors' GPUs, with Argonne, Ornal, and NERSC. Just want to mention that Kokkos is currently working on various backends for the support of these different kind of GPUs. There's a HIP backend under development for AMD and a SYCL hybrid for Intel. Additionally, there's an OpenMP target backend that can be used with AMD, Intel, and NVIDIA being developed. Shown here are the links where you can get more information if you're looking for some additional examples or any more information about the tools or kernels, and the tutorials are shown here. Additionally, there's a Slack channel for user support that anyone can join to get help. And with that, I'll end my discussion of Kokkos and move on to the RAJA programming model. The slides presented here are from Rich Hornung from LLNL and the RAJA team. RAJA is a library of C++ extractions that allow you to write portable single-source kernels that run on different hardware by recompiling. It encapsulates the application source code by putting all the model-specific implementation details into a header file. And it has support for a variety of parallel programming patterns and performance tuning. The major design goals are usability and developer productivity. We want to maintain as much as possible single-source kernels. RAJA wants to be easy to understand, allow for incremental adoption, and to not force major disruption into application source code when porting to a new system. It does this by promoting clean encapsulation and easy to parameterize execution. There are several open source projects related with the RAJA project itself, such as the user guide, where you can find information about all the policies and some examples on using RAJA. There's a RAJA project template, which can show you how to get RAJA installed and be usable by your project. A RAJA performance suite, which is a set of benchmark kernels for assessing compilers and the performance of RAJA. And Chai, which is an array abstraction library that automatically migrates data as needed based on RAJA execution context. So I'd like to cover a simple loop execution. Shown here is our beginning example. It's a simple DAXP, where we iterate from 0 to n, performing our computation. Now, to port this into RAJA, we do a transformation into a RAJA-style loop, and there's a few differences here. But additionally, we have the execution policy and iteration space that need to be defined. So we will define which execution policy we're using and the range segment or the iteration space that we're going to go through. These definitions attempt to go in a header file to make it easy to port from one execution space to another. You'll notice that the body stays exactly the same. And ideally, the RAJA-style loop does not have to change when you port to a new device, only the execution policy and the iteration space. RAJA loop execution has 4 core concepts: execution template, the policy type, the iteration space, and the body. Going a little more about the execution policy type, this is where you define what you're going to be running on. So OpenMP, CUDA. You'll want to use OpenMP for data and CUDA for cooling. Additionally, you can execute over SIMD lanes. Next, we pass in an iteration space object to let us know how we're going to iterate over our work items. And finally, we have the loop body, which is cast as a C++ lambda expression. There's many execution policy types. Shown here are several of the examples, such as SIMD, OpenMP, and CUDA, along with OpenMP target, and there's additional ones under development. So let's look at a reduction now. Reduction is common and important. Shown here, we're going from 0 to n, reducing into our dot product, similar to what we saw with the Kokkos presentation. Now we need to create a reduction object to hide the complexity of this parallel reduction. Shown here, this is our dot. Now this reduction object requires a few different things: a reduction policy, a reduction value type, and an initial value. The reduction will be added into, but you cannot access the reduced value inside of the kernel. And there's multiple things you can use: plus, minus, min, maxes. After the loop is run, you're able to get the final value by using the get method. An important note is that the reduction policy must be compatible with the loop execution policy, but this is fairly straightforward. You see that we have an OpenMP reduce, a CUDA reduce, and a sequential reduce, and these match to the execution policy that you want to use. Shown here are the common reduction types: sum, min, max, and then also a min, max with the location. Next, I'll talk briefly about the iteration spaces in Raja. First off, there is a segment that you can pass in as an iteration space. This is a set of loop indices to run for a kernel. There are various types we'll discuss briefly later. And additionally, you can do a index set, which is a container of many segments that can be of various types, shown below, where we have a range, then a list, then a stride 1 range. Now, a range is a continuous sequence of indices, shown here from 0 to n. But there's also the option for a strided segment, which goes from 0 to n with a stride of 2, so we go from 0 to 2 to 4. And this strided segment can also allow for negative indices and negative strides. So here we're going to iterate from n-1 to -1 with a -1 stride. Now I'm going to touch briefly on the way you perform nested loops inside of Raja. You do so by using the Raja kernel API. It's designed for composing and transforming complex kernels. We'll talk about each of the elements here. But just like the Raja forall, it uses 4 basic concepts. Execution template. Now we're using a Raja kernel instead of a forall or a parallel reduce. And execution policies. Instead of a single execution policy, we're now able to have many. The same goes with iteration spaces. And even the kernel body can include multiple lambda expressions. Each loop level has an iteration space and a loop variable. So each statement, these are 4 statements, have an initial parameter which indicates which index it applies to. 0 equals to column and 1 equals to row. And then we have the execution policy that we're going to use. We execute over rows, execute over policy or over columns. Now, to give you a flavor for some of the very advanced things you can do with these Raja kernels, we can very quickly and easily swap our execution from our outer row being the row loop to the column loop, simply by swapping these 2 statements without making any changes to the kernel code. Kernel policy is comprised, it's a simple DSL that relies on standard C++ support. It's built from statements and statement lists. Statement is an action, such as execute a loop, as we saw before in our statement 4, invoke a lambda, or synchronization, such as CUDA sync threads. A statement list is an ordered list of statements. So here we have a for loop that executes a lambda, then executes a for loop with an additional lambda on the inside. Some application considerations to take into mind when porting to Raja or any performance portable programming model. You want to define type aliases and header files. This makes it easy to make changes without disrupting your source code. And try to align things into classes of loop execution or kernel execution. Shown here is an example where we define the execution policy we're going to use when looping over elements. And then we use that same policy in all of our loops that do work on each element. Now, performance portability is going to take effort. This is not a panacea. It's an enabling technology to make it simpler and easier to get running on a new platform. And there's a few things to watch out for. You want to make sure to maintain thread safety. This is critical importance of any parallel application. You want to understand your characterization and performance of your loops, which is why you want to utilize good tools to understand your code well. And any memory motion and access patterns are going to be very critical, and this is true for CPU code along with GPU code. Well, we aim to not have to change the kernel. Sometimes there may need to be a change because of the need for finer-grained parallelism, and sometimes you need to change the algorithm that you're using to ensure that you get correct parallel execution, or make various changes such as recasting some patterns as reductions or scans. Now to wrap up, you can find all the working examples and tutorial at Raja GitHub. Look inside the example and exercises directories. There's also the user guide shown here, which is linked to from the GitHub itself. And the related software that we touched briefly upon earlier is also available, the Raja Performance Suite, which tracks how well the Raja code is doing compared to the native execution. This also provides many kernel examples for using Raja. And Chai, which once again provides software data copies from different memory spaces. It's designed to work from Raja from a very high level, and it can, in theory, be used with other Lambda-based C++ abstraction layers. Thank you for your time, and please reach out if you have any questions. I hope you'll have fun experimenting with the Kokkos and RAJA programming models.